Hello, everyone. Welcome back. Today, we want to talk about the present value of annuity. So, in a past video, we talked about the future value of an annuity, which often is involved in something like retirement account, where you're paying so much, possibly a month or in some periodic way, to get a certain amount in the future. Now, we want to talk about the present value, which is basically you have maybe a debt of some kind or a certain amount you have right now, and then you want to basically be able to pay that off in the future. So our goals are basically in part to know when to understand the difference between present and future values of an annuity, know which formulas to use, then be able to calculate then present value of an annuity. So the present value of an ordinary annuity, remember that an annuity is a sequence of equal periodic payments. And an ordinary annuity is a payment that is made at the end of each time interval. So the present value of an ordinary annuity is the sum of all the payments plus all the interest earned, and is given by this formula, similar to the future value annuity formula, but it's still a bit different. And where PV is what's called our present value, then PMT is our payment, I is our interest rate per period. For example, I is if your interest rate is given in an annual interest rate and you're paying off something monthly, then you have to convert that to an interest rate per month. And then finally, N is the number of total payments or periods. Now, some kind of guidelines on when to use which formula. So use the future value of an annuity formula if you're making payments to get a certain total amount in the future. Example, once again, like retirement fund. But use this present value of an annuity formula if you're paying a total amount now, or if you bought something like a car payment or a house, and then the payments are made to pay off the total, or if you'll receive payments in the future. Example, that would be a house loan. So you buy a house or a car, and so then you have to pay off monthly payments, and then those payments contain or basically pay off not only the amount of the loan, but then also the interest. Because the interest is how the bank makes money. That's how they decide to give you a loan, is you pay a certain amount of interest. And so those payments then contain not only the amount of what the house or the car is worth, but then also the interest as well. So let's take a look at some examples over here on the right. Let's see what sort of situation we have. So number one, it says, American General offers a 7-year ordinary annuity with a guaranteed rate of 6.35% compounded annually. How much should you pay one of these annuities if you want to receive payments of $10,000 annually over the 7-year period? So once again, this is going to be a present value of annuity, not a future value, because in this case we're basically creating kind of like a amount that's going to be paid off to you at certain periods annually, like $10,000 annually over a 7-year period. Okay. Now it's possible you still might pay that off in payments of basic stuff as a present value, then a certain amount you're going to have now, and that's going to pay you off later. In some ways, it's kind of the opposite of it's kind of reversed like a car loan, where you'd pay off the car company monthly. Let's take a look and see how this works. So if we're going to do this present value, and let me draw a menu. So let's figure out what we have. So the question then is, how much should you pay for one of these annuities? What we want to do then is want to find the present value, the PV. Okay, so what we have so far, we know, is our payment, as it says, is going to be $10,000 annually, or that's of course per year. Then our interest rate, I, is going to be basically our interest rate is a decimal 0.0635. We won't round that off. And then that's going to be divided by the number of periods per year. In this case, it's only one. It's also annual. And so that's just going to be 0.0635. And then our N, and since it's going to be for 7 years, so N, and making these payments are made to us annually, are going to be 7. Okay, so let's plug all that in. Formula. So our present value is going to be 10,000 times 1 minus, and then 1 plus I, so 1 plus 0.0635 is going to be 0.1.0635. So 1 plus that, 1 plus I, that's it. And then raise the negative end, the -7. And then this is all divided by I. Remember, I is 0.0635. Okay, now we're actually going to use Desmos to actually calculate this for us. So give me a moment to set that up. And I think I already have, I've already done some calculations. Let me just create another Desmos window. You can also use it to calculate things, not only graph, and it's also kind of good for demonstrations in these ways. Okay, so let's put in what we have. So our payment was 10,000, little space. Then I'm going to use parentheses here, so we have to divide the whole thing. 1 minus, then the 1 plus the interest is 1.0635. Then we're going to raise that to the -7. I get out of the exponent, then use parentheses, we're still not there. Then we're going to divide that by I, which is 0.0635. Okay, and so what that says, and this is 55,135 point, rounded nearest cent, 0.98. So that's our amount. So then the present value, it says, around the nearest cent, is $55,135.98. Okay, and so what that means then is that for this kind of annuity, so maybe this is thinking it's kind of another way of doing a retirement account. Instead of actually paying into it, you're going to create, maybe you like a lump sum in there, then this is going to generate interest. It's going to pay you off then $10,000 a year over a 7-year period. Okay, if you notice then, of course, $10,000 a year for 7 years would be $70,000. This is about $15,000 less than that. So that's the rest is made up from the interest. Then you're actually generating at this rate, you're generating about $15,000 of interest over that amount of time. And so then that would actually be, in that sense, cheaper than actually just saving it and then putting like in just maybe like a savings account and then drawing it out later in retirement. It's also possible, as I said, that you might actually then structure like another ordinary annuity to actually pay into this to get that amount. That's something you could also do, or just put in as kind of a lump sum. Okay, so that's the idea. So in that case, we want to find the present value, what you needed to accomplish that. All right, let's take a look at our second example. All right, so this one says, the annual interest rate on a credit card is 22.99%. Once again, that's annual interest. The minimum payment is $25 is made each month. How long will it take to pay off the unpaid balance of $860.22? So once again, it's kind of collect, as we're trying to find, I want to find the time. And one way to do that then, if we find the number of payments, then we can find the time. So let's find the number, it's supposed to be an N, of payments needed. Okay, so first off is kind of look at our formula and see what we have so far. So our unpaid balance, this is the amount we're going to pay off. And this is definitely see where it's much more like an idea of like a car loan or home loans. This is a debt right now you have, and you want to be able to pay it off with $25 a month. All right, so the question is how long does it take to pay off? So our amount, our present value, we have to pay off is the $860.22. Our payment, in this case, we know that's the minimum payment. It's going to be $25 per month. And then also our I. Now this is annual interest rate, but you're going to basically it's being essentially interest rate is being done per month, and so that's going to be right. This is a decimal 0.2299. Leave that as a decimal, and then divided by 12, and let's see what that's going to be. And this we probably will round off because I recall this is a kind of a longer decimal. So 0.2299 divided by 12. and right. So that's actually a really long decimal. So I'm just going to write that as, I think I'll do about 5 spaces. So 01916, round to 5 places. So that's our I. Okay. Now, then, of course, then our n is what's unknown. We want to find the n. So let's plug all this in, our formula, and we're going to have 860.22 is equal to 25 times 1 minus, and this will be 1 plus I. So I is this. So 1.01916 raised to the negative n over I, which is 0.01916. Okay, now if you notice, what we're trying to find is in the end. So a couple ways we can do this. I'll show in this one, I'll show you how to do this by hand by using logarithms, but also in the future, another example in this lecture, I'll show you how to use actually Desmos to do this, or any kind of graphing calculator or something like that. So let's actually solve this. Let's do a few things first before we do that. Okay, so let's go ahead and divide both sides by 25. So 860.22 divided by 25, and that's going to be 334.4088. And leave it like that. That's equal to this 1 minus 1.01916 to the negative n, and divided by 0.01916. Now I'm going to multiply this by this, multiply both sides by that. And so that's going to be times this times our denominator, 0.01916. Now this I will also round off. What we have so far is point. I'll also go to 5 decimal places. 65927 is equal to this 1 equal to 1 minus 1.01916 to the negative n. Okay. Now, so what we're doing, our goal is to basically get this term with the negative n, get this thing raised to the power of the negative n by itself, and then we're going to take logarithms to basically get the n out of the denominator rather than the exponent. Okay. So subtract 1 from both sides. And so that's going to be negative 0. Once again, to 5 decimal places, 34073. Okay, now, of course, multiply both by a negative number. And so that's going to be 0.34073 is equal to 1.01916 to the negative n. Okay, so we're getting closer. Now, so here, we can use logarithms, and you can use any log you want, but you have to use natural log, which is ln, or log, which is log base 10. Those are the ones that most likely be found on your calculator. So I'm going to actually take the log of both sides, natural log. And so that then will be ln of 0.34073 is equal to ln of 1.01916 to the negative n. And for rules of exponents, I can bring this negative n down front. And so that's going to be natural log of, once again, this, our left side still the same for now, 34073 is equal to negative n times the natural log of 1.01916. So once again, that's from the rules of logarithms. Write that better. I can do that. Now, this is just a number, and this is just a number. The only thing that's unknown is our n. Let's basically divide both sides by this natural log term, and I'm also going to turn this around. And so this is going to be negative n is equal to natural log of 0.34073 divided by the natural log of 1.01916. It's a little more like a 9. And also I'm going to go ahead and, since just don't have to write this step again, let's make this multiply both sides by negative, and we're going to have this. Okay. Now, once again, I'm going to use Desmos to help us figure this out. Hang on, I'm trying to. There we go. Yeah. Okay. Now let me type that in, and actually let me write it down just a moment. So now let's go back to Desmos, and we'll use Desmos to help us calculate this. Okay, so it was going to be negative. Now just type in ln and then use parentheses, and so the numerator is going to be 0.34073. Then that's divided by ln, and once again parentheses of 0.01916. Okay, make sure everything is right. And so that tells us then, just a moment, that shouldn't be. All right, let me go back just a second. I think I. Oh, I realize. Yeah, okay, that's what happened. Sorry, this is a 1 point that. Yeah, I wrote that. Yep, I wrote that down wrong. So that's a quick fix though. But yeah, always be careful. So clear me off. This was a negative. It shouldn't be negative. I realized what I had was this should be a 1, not a 0. Do that exactly. Okay. So what that gives us then is, okay, hang on. That doesn't look just a moment. Right. No. Okay. That's okay. Good. So that's actually not, I looked my notes. Is actually is not what I had in my notes, but this should be correct. Okay. So what do we see is this is about 56.7. Let's go with that 56.7. So this n is equal to approximately 56.7. Now 56.7 what? So remember we're paying this off monthly. How much we're going to pay each month. That means this is going to be over 56.7 months. And if you just divide that by 12, and that's about also approximately about 4.75 years. Okay, if you just pay the minimum payment, because also what you're paying off is not only the payment itself, but also the interest. Okay, so that's actually about almost 5 years. That's not really, as you see, that's not the best way to do it. It's better to pay off more. And so that's one thing also, as you expect in general, these things you'll see, especially when we talk about mortgages. The next example, you'll see that one of the reasons why when buying a car and buying a house, you want to make as large down payment as possible, is that's going to reduce the amount you pay in total. Okay. Although it can be really tempting to try and, get the lowest monthly payment. So it's better if you can to make a larger down payment to begin with. So you're going to wait maybe some amount of time before you buy a car or house if you can, and then where you can get a larger down payment. Okay, what this says then is you can, under these conditions, making the minimum payment of $25 a month, have this balance with this interest rate, which is a really high interest rate, but that's not entirely unusual for credit cards. Then it's going to take you almost 5 years to pay it off. So you can see that's definitely not the way to go if you can help it. Okay, last example here is this says a family bought a house for $300,000 and they'll pay it off with a 30-year mortgage and a 6% annual interest rate compounded monthly. So I want to find two things. One is first is find the monthly payment and the total interest paid. Let's start there, then we'll find the rest of it. So for part A, and I want to find the monthly payment. So our present value, that's how much we're buying of the house, is $300,000. Okay. Then, so our interest rate, our I, is going to be, and once again, this is going to be compounded monthly. It's the monthly interest rate, annual interest but compounded monthly. So 6%, which is 0.06 divided by 12. And that won't be a terribly bad decimal. No, that's going to be about 0.005. Then also our N, what is our N? So our N is the number of payments. Okay, so the number of payments we're going to make in total. So it's going to be doing this paying monthly, the monthly payment, 30 years. That's going to be 30 times 12. So 30 years, 12 payments each year. And so that's going to be 360 payments. Okay, so let's plug all that in. And so this then, now here, if you notice, where a formula is structured, it's actually set up for the present value is equal to the payment. So what we have to do is essentially solve this for the payment. What you do is mathematically, you just multiply both sides by the reciprocal of this. And so what we get then, we have the payment is equal to the present value times I over 1 minus 1 plus I to the negative n. Okay, so that's how if we actually want to solve this formula for the payment. All right, so now let's plug everything in. We plug everything in. We have $300,000 times I, which is 0.005. That's our interest rate per period. And 1 minus 1 plus I, which is going to be 1.005, raised to negative 360. And once again, we're going to use Desmos to help us out and calculate this. Let's go back there. All right, so our total value, $300,000, then times I, which is 0.005, divided by 1 minus 1.005, then raised to the negative 360. Okay, and we see there our payment is about $1,798, and there is cent 65 cents. And so then our payment, once again, is just that amount. So $1,798 and 65 cents. So this is your monthly mortgage payment in that case, so per month. Now, the second part of that question was, what's the interest? So the interest, total interest, is, so basically as we compare that, if we do 360 of these payments, then subtract the present value, and so that's going to be the total payments, the total of the payments. Okay, so then minus the present value. So if we do that, we have $1,798.65 times 360, right? 360 of those. And you see this is going to be quite a bit more than $300,000 a house was worth. So if we do that then, let's go back to Desmos and do that so we can see it easily. So our monthly payment is $1,798.65 times 360 times 360 payments, and you see that's $647,000. So we're paying way over twice as much. The total is going to be here. So then minus the $300,000, and our interest, the interest, what you're paying essentially to the bank for this loan, is going to be $347,000, $347,514. Which is a lot. Okay, that's why, once again, you want to try and make large monthly, you want to try and make as big a down payment as possible as you can. Okay, hold on just a minute. Okay, I apologize. I'm about out of space. I'm going to actually have to. Give me just a moment. I'm going to have to copy all this and move it down because I'm almost out of space for the rest of the problem. Okay, I'll just start a new page. Okay, so now I'm going to go back and just paste that, hopefully. Okay, good. I've done a little bit of kind of housekeeping. I should have done that before, but I just wasn't thinking. All right. It's actually a nice tool. I can erase things much easier with this. I'll make sure I got everything that I need up here. I did. Okay. All right, almost there. Okay. Now that was part A. So we found a monthly payment, then also found the amount of interest that we're paying, which is more the amount of the house sold for. Of course, this is also over a 30-year period, so you don't notice as much, but still, that's a lot. Okay. Now, make sure I have enough room. Let's go back here. All right, so part B. What does part B ask? And part B is asking if we change our monthly payment, what effect will that have? Okay. So part B says, suppose the family decides to add $200 to each payment, starting with the first payment. How long will it take then to pay off the mortgage, and how much interest will be saved? Okay, let's take a look at that. So we're going to add $200 per month to the payment. I'll just say from the beginning. Okay, from the beginning. So the new payment then is the other previous payment is 1798.65 plus $200, and that's going to be then we'll put that as PMT. That's going to be $1,998.65, so almost $2,000 a month. Okay, now with that, then we want to find the number of payments. Needed. And to find out how many payments we're going to need to make that happen. All right, so we have everything else we need. Let's go back and take a look on the previous page. And so all this other, of course, the N, the present value is still the same. The I is still the same. Now we know the payment. The only thing is unknown is the N. So it's kind of like the second example we did, except we're actually going to do this a bit differently. And so if we plug this in, and this is going to be then our present value formula. So it's going to be $300,000. That's our present value, is equal to our payment, which is 1,998.65 times 1 minus 1 plus I. This is 1.005 raised to the negative n. And once again, this is over I, which is 0.005. Okay. Now, so this is very much like the second example we did, where you need to solve for n. What we're actually going to do then is actually use Desmos to help us out with this. Okay. So what I'm going to do now is I'm actually going to subtract the $300,000 from each side. Okay. What that's going to leave me with then is I'm going to call this y then is going to be equal to this 1,998. You don't really need the dollar sign there. In fact, I don't think I'll just get rid of that. 0.65 times this fraction, 1 minus 1.005 raised to negative n over 0.005 minus 300,000. Okay. Well, what we're looking for is a place where these two things are equal, right? That's what the solution is going to be. A solution to any equation is the value that makes it equal, not that makes it true. So essentially, where is this side going to become $300,000 when I find that n? Okay. And so what this does is I've essentially made kind of like a function. Okay. So when these things are going to be, these halves are going to be equal, then this at that solution point, the value that's going to make this equal is going to be the value that makes this whole thing 0. So when y is equal to 0, n is the solution. And also the way I set this up then, I'm actually then going to use this, put this into Desmos then. Okay, so let's go back to Desmos. I can graph this. So we'll put y equals you can. You don't have to, but I think I will. And it's going to be 1,998.65 times 1 minus 1.005 raised to the negative x. In this case, x's are unknown. Okay, then divided by 0.005. Now that's not it yet. You still have to do this. So then minus 300,000. Okay. Now we actually looks like we need to kind of recenter our graph here. If you notice we don't see anything yet, it's probably because it's kind of far out. Because remember, this is still going to take this up to 10. This is still going to take many payments to do. Let's zoom out. Keep zooming out. Yeah. So where this is 0, it crosses the x-axis is our solution. And actually, nice thing about Desmos, it actually does that. So you click on that. Okay. And that value is 278.358. Okay. 278.358. So that tells us then that number, that's the number of payments we're going to need to pay it off. So 278.358. So this is approximately, I'll just call it 278. Let's round down because basically, potentially you'd either one, but eventually then for that last payment, you either add some extra amount to that last payment or then do one more smaller payment, making up that part to finish that off. But basically, it's saying 278 payments. Okay. Now compare that to 360, you can see that's quite a bit less. Okay. So just by adding $200 a month, we're actually saving quite a bit on payments. And the last part of that is the question is how much are we saving on interest? Okay, remember this is the interest we paid if we do it the original way. All right. So once again, in the same way, let's find the amount of interest we paid in exactly the same way. So the interest, and once again, we're just going to call this, well, for this, let's just go ahead and call it 279 so we can round up. Okay. It's not going to be, well, let's see. Trying to decide. Actually, leave it there. We'll use this exact amount. That will give us more precisely then. Okay. So the interest is going to be the payment, which is going to be, first I'll calculate the total amount that's paid in, which is 1998.65 per month times 278.358. Let's go ahead and use that answer there. Then minus the 300,000. Okay. Let's going to use Desmos for that. Then that's going to tell us then the amount of interest we paid. And that way we can actually find the amount of interest we've saved. Well, let's calculate that. So 1998.65 times 278.358. Okay. You already see it's less than minus $300,000. Okay. And that amount then is 255,340 point, and there's cent 22. 255,340, sorry, 256,340 rather. 256,340.22. Okay. So this is once again, so $256,340.22. Now the interest saved is then going to be this previous interest, 347,514. Apparently that was 0 cents, just minus this, so 256.3 or 0.22. And I'll just do that on my calculator here by hand. Right. And that comes out to be about $91,173.78. Okay, so that's how much interest you've saved by, in this case, just adding from the very beginning, adding $200 a month to your interest payments. You've saved a little over $90,000. So once again, that's the advantage of not only having a larger down payment, but also doing a larger monthly payment. So that's why people say, like a car loan, it's better to do a shorter car loan, even though you have higher payments, than it is to do a longer car loan in the future, because you'll be paying less over time. But once again, it depends on what you're able to pay and what you want to be able to pay per month. And those are also the considerations have to be made into that. Okay, so what we learned today then is how to use the present value of the annuity formula, the difference between the future and present values, and then basically being able to calculate basically payments, the amount of a present value, the amount of a payment, and also the time or number of payments required to get to that. Thank you. Have a good day.